Good morning, everyone. As I said, Roger Penrose, that he showed some evidence that there was a universe before the Big Bang, and now he also have a theory which is called Weyl tensor hypothesis. And before we talk about the Weyl tensor, we need to talk about the Riemann tensor, and you need to have some knowledge of tensor and covariant derivatives. In cosmology, you don't use partial differentiation because the reason is your basis vectors are going to change from place to place. So for that reason, you have to use covariant derivatives. And you have to know what a covariant derivative is for this webcast to be understood. And if I just lightly, say what it is, we cannot use Cartesian coordinates. As soon as you start using some other coordinate for curved surfaces, your basis vectors are going to change. This change has to be captured, and the partial differentials cannot capture that change. And that can be captured using the covariant derivatives, where you have Christoffel symbols would be involved. So let's look at Riemann tensor. And if you look at a parallelogram drawn on a curved surface, and we need to capture the curvature on A to B, B to C, C to D, and D to A. So this curvature, when you go take a vector, actually in Riemann tensor we take three vectors, go A to B, B to C, C to D, and come back to A, the vector would change. Now in a parallel surface, the vector will not change, but in a curved surface, the vector would change. So we are going to call A dash vector. It's not the position is the same. So the commutator of AB is A times A dot B minus B dot A. This is a commutator that appears a lot, and we have to find that. Now the commutator of two numbers, let's say 5 and 3, will be 5 times 3 minus 3 times 5 would be 0 for numbers. I think it is 0 for complex numbers too. I'm not really sure. I think yes. For numbers this is 0, but this is not 0 for functions. So let's look at a function. Now here we are using the partial derivatives and fx. So dou x and fx. So this is A and this is B. So A times B is dou fx over dou x. That would be A dot B minus B dot A fx times dou x. So this is pretty understandable. And then we multiply this by a vector v. So dou fxv over dou x minus fx times dou v over dou x. So here you have a two functions under the dou x. So we can take fx times dou v over dou x plus v times dou fx over dou x. We have to do it, turns into two terms like this, and then you have this term fx times dou v over dou x. This cancels out with this one, so you would end up with v dou fx over dou x. That's the commutator. I think that's pretty understandable. Now we want to capture the curvature from B to C, C to D, and D to A. So let us take a vector and we transport from C to D, and that would be VC minus VD. And then we transport a vector from B to A. The change is VB minus VA. So C to D changes VC minus VD, B to A changes VB minus VA. So VC minus VD, so VC minus VD minus VB minus VA minus VB minus VA. So this one gives the curvature in AB direction, this one gives the curvature in CD direction. And if the surface is curved, if this is not curved, it will be 0. But if the surface is not curved, this value is not going to be 0 if the surface is curved. So that value is going to be the total transport go around and VA minus VA dash. Now A dash and the position is the same, but the vectors will be different. So that will be called dV. So first we are going to find, so we have to find this full term. So first we are going to find VC minus VD. VC minus VD, first we are going to find that the rate of change is W or WX. We are still using the partial derivatives, but we have to use covariant derivatives. This is just to explain we are using this. So the rate of change in W is W or WX. In reality, the rate of change is covariant derivative. So I'm going to use it here. So the rate of change W over WX times dx and times the vector. Now we cannot, as I said, for curved surfaces, we cannot use partial derivatives. We have to use covariant derivatives because of the rate of, there's a rate of change in the basis vectors. This rate of change in the basis vectors has to be captured using the Christoffel symbols. So our covariant derivative mu would be W over WX. This would be the partial derivative plus the covariant derivative. The covariant derivative have three indices according to Einstein's summation notation. You would have nu, mu, and the direction that the basis vector is located. So you would have three indices. Now we are just trying to understand the concept, so I'm not going to go into Einstein's summation convention here. So we're just going to ignore the indices. So VC minus VD is delta, double mu. I'm going to replace with the covariant derivatives. So it will be covariant derivative delta mu dx mu times v. So basically I just replace the partial derivative with the covariant derivative, and then there would be that, and then the VB minus VA, we could do the derivative on top of this derivative. That will be the curvature on B, this curvature here, VC minus VD to be this curvature here. That's also a covariant derivative. Again, if you are going on a curved surface, this always has to be covariant derivative, because you cannot find a coordinate system that the basis vectors will not change in curved surfaces. You are going to end up with a situation where the basis vectors would change, and then as soon as the basis vectors start to change, then you are going to see Christoffel symbols. And once you have Christoffel symbols, you cannot use partial derivatives, and you have to go to covariant derivatives. But I just started out with partial derivatives to show that we have to go to covariant derivatives. So basically this term captures the curvature from C to D, and this term captures the curvature from C to D to B to A. So the first term, in this case the first term is here, delta covariant derivative mu term, that would be capturing the curvature this way, and the covariant derivative dx nu term capturing the curvature that way. So you capture the full derivative, and that would be your full curvature. And this is I just showing the Christoffel symbols here. So this is your Riemann tensor, that would be the full curvature. So the full curvature is due to the mass, that would be the Ricci tensor, and due to the gravitational field, and that would be the Weyl tensor. And actually due to the gravitational potential, even though there is no mass, Hermann Weyl came up with this idea, which is accepted, that there would be a tensor, and that is part of the total curvature. Now again, as I said, I did not put all the indices. There will be 3 indices here. There will be mu, nu, and the you could call it lambda. That would be the third index, would be the direction of the basis vector at that location. There could be number of basis vectors, and so there would be a total number of Christoffel symbols equals to the basis vectors in that point. And this is as per these indices, not as per Einstein summation convention, because just for demonstration purposes, this would have 2 indices and this would have 3 indices. So what is Roger Penrose saying? So the Roger Penrose is saying, during the Big Bang, of course, everybody agrees that there is no mass. It was radiation. So the Ricci tensor, that is due to the mass, gravitational bodies would be 0. But the Weyl tensor, the gravitational potential tensor, would not be 0. And according to Roger Penrose, and this Weyl tensor would be suppressed during the Big Bang. So that's the reason why you have a low entropy. And this theory is not really accepted, but that's his theory. And the Weyl tensor got activated after the Big Bang, sometime after the Big Bang. Again, there is no evidence for any of the things that he's coming up with, but it's a theory, and you could you'll be able to test later on down the road. So I will try to do another article explaining more. I just did this part quickly, just to explain what the Weyl tensor is. So the Weyl tensor is part of the Riemann tensor, a part of the full curvature tensor, and Riemann tensor is part of it due to Ricci tensor, and part of it is due to Weyl tensor, due to the gravitational potential. And for fully understand this, you need to know the tensor calculus and differential geometry and Einstein summation convention to fully understand these things. But this is some just a very, very low level introduction. So what Roger Penrose is saying, all right, let's see. So there has to be a Weyl tensor from the past universe. Now, Penrose is saying that tensor gradually deteriorated once the black holes are all gone. All the matter is gone, that tensor is gone. There is no gravitational potential due to radiation. Now, I don't know whether that's true. I never seen anybody else talking about it or saying that it's true or false. So I don't know whether it's true or false. So, but this part is for sure. Ricci tensor would be gone when in the past universe, when all the matter is gone, Ricci tensor would be gone. So that everybody agrees, I think. And the just because there is no matter, there still could be a gravitational potential. I don't know. I'm not that type of expert. I have no idea. But according to Penrose, that tensor also would be suppressed. So there is no gravitational masses, and there is no gravitational potential. And that from the past universe. So when the past universe carried forward to the next universe, to the Big Bang of our universe, then there was no Weyl tensor. So it was already suppressed. So the gravitational potential was 0, so the low entropy happened. Now that part, I'm not sure how, he doesn't explain that. And there were papers he has written, and honestly, I didn't really understand the mathematics of it, so I cannot tell you how would the suppression of the Weyl tensor would give rise to low entropy. I don't know how. I didn't understand, or he didn't really explain that properly, whatever it is. So basically, then you would have a situation where you have the Big Bang. Everybody agrees that there's no Ricci tensor, and not everybody, Roger Penrose says there was no Weyl tensor either. So that leads to low entropy. That part I did not understand. And let's say not too many people have said it is true. So I would say it's not really accepted. And according to Penrose, Weyl tensor, not the Weyl, Ricci tensor would be activated once the radiation turns into mass. So that part, we all understand that part. Once you have gravitating mass, then you have the Ricci tensor. Now, when did the Weyl tensor get activated? I looked through Roger Penrose's papers. He don't say that. He don't say what point the Weyl tensor get activated. It doesn't. I don't see it. And he don't believe in inflationary theories. So it would have activated at a very early stage if there's no inflation. Now I'm speculating what his theory is. It's not very clear to me. And when the Weyl tensor got activated after the Big Bang. Anyway, I will try to do another video with more explanation. And thanks a lot for listening.